So let's look at the only new information as far as system representation is concerned for control systems 3, and that would be the state variable representation. Remember, we said in a few lectures back that there are two ways fundamentally of modeling control systems or plant or process, and it's based on the natural science or the physics of the plant, as commonly called, or you can use system identification techniques, that is experimental data, if the model is too complex or if the process of modeling using natural science would take too long. So we said there are two ways in which you can model, which is based on the natural science or the physics of the model or system identification. And we have since looked at different types of systems. We have looked at thermal systems, electrical circuits, LRC circuits. We have looked at mechanical systems in the form of mass spring dashboard systems. We have looked at also fluid flow systems. And given all of these types of systems, given the fact that you can model them using different maths of physics, the underlying physics, you can represent the model generically in three different ways. And we said the three different ways you can represent the models are: you can represent them using differential equations, dynamic differential equations, and then you can represent it using transfer functions, or you can use what's called state space representation or state variable representation. So this lecture is all about how you represent your system using state space representation or state variable representation. Now we will look at what the state variable model of a dynamic system is. We have already reviewed matrices in preparation for that, how the maths of the matrix works. So if you have not done that yet, please go to the previous lecture to review how the matrices work. And we will look at a simple example of state variable representation. We will look at how you do linearization with state variable representation, and then how you can convert between effect from the state variable to the transfer function model for a system. Now, for a generic nonlinear process, with input ut and output yt, that process, according to state variable representation, can be represented by a set of differential equations. The first set is the ordinary differential equation of x. X, we call it a state vector of state variables, or a vector of state variables. So we assume that the system has a number of input variables u of t, and a number of output variables x of t. And internally, the input of the system influences the behavior of the system by influencing its state, and the state is represented by a set of variables which are called state variable x. So the way in which the system moves is described by g of x, which is the state differential equation. Now, in order for you to get an output, the output of the system are also linked to the internal state and the input of the system. And so, this relationship is captured by a function f. So function f captures the output equation. Now the current values of x, the state variable model assumes that the current value of x and the input and the modeling equations f of g can be used in totality to determine the future state of x as well as the output variables y. However, in this course we are going to be concentrating on the use of linear systems only. Because of that, the representation of a linear state variables model is slightly different. So a state variable model for a linear system is represented by a set of 4 matrices A, B, C, D, and the model or the state differential equation G becomes a differential equation, a linear differential equation in x and u. X dot is equal to A times x plus B, and then the output function f, becomes the output matrix equation, which is linear in the state x and the input u, and the output becomes cx times du. So given that the system state variable model is distinguished by the inputs, the states, and the outputs, it's clear that then the state variable representation can easily model a multi-variable system, that is a system with multiple inputs, multiple states, and multiple outputs. But for the purpose of this course, we shall focus or restrict ourselves to single input, single output system, normally called SISO systems. And because we are not going to be dealing with generic non-linear systems, we're going to be dealing with linear systems of this form. We will linearize the equations of the system, that is g of x u and f of x u, using the Taylor series linearization method that we have adopted previously in the previous lectures. So for example, a two-stage single input, single output system would have two states, x1 and state x2, and the A matrix of this SISO system would be 2 by 2. So the matrix would have dimensions 2 by 2, and the B matrix would have dimensions 2 by 1. It has 2 by 1 because there are two states and there's only one input. So the B matrix, as you can see here, it links the differential equation of the state with the input. So it's going to be 2 by 1. And then the C matrix is going to be 1 by 2 in size because the output is 1. Because you can see here, C matrix, it links the states with the output, and the output, there's only one output and two states. The D matrix, similarly, it's going to have to be 1 by 1. The D matrix is going to be 1 by 1 because the D matrix links the input U, which is a single input, to the output 1, which is a single output. So for the state variable representation, we're going to deal with systems represented in this form. X dot is equal to AX plus BU, and Y is equal to CX plus DU, where A, B, C, D are matrices. For the purpose of following the lecture smoothly, I advise you, if you have not, to go and review your matrix mathematics. And there is also a lecture video which has been posted about the important information that you need to remember regarding the manipulation of matrices. Now, as an example of a state space representation of a system, I want us to consider a mass spring dashboard system shown in this figure. So the system is of a mass which is attached to a spring, and it has been pulled by an input U, the force U of T. So U of T is the force, and it moves. Its output is the displacement Y of T, and the mass has friction with the wall, and the friction with the wall acts as a damper. X as a damper in the sense that the friction is proportional to the velocity. Now the task here is to create a differential equation of the system, and then from those differential equations we need to then create the state space model representation of the system. Now if we draw a free body diagram of the mass, we will see that this is the direction of positive displacement, which is y, and the forces acting onto the mass are going to be the pulling force, which is u, the resisting force of the spring, and then the resisting force of the damper, which will go against the motion. Now the differential equation therefore becomes mass times acceleration using Newton's law of motion. Mass times acceleration is equal to the sum of forces. So this would be the pulling force minus the force due to friction minus the force due to the damper. And so this gives us m, the second derivative of y is equal to u minus ky minus b k dy dt. Now having noticed that we now have this as a differential equation, so we need to translate this differential equation to a state space model or state variable model. Now in order to create a state variable model, we have to choose arbitrarily our states. So we can pick x1 and x2 as our states, and if we do that, then we let the velocity become state number 1 and the displacement becomes state number 2. You can swap this, the model that the state-based representation that you will get is going to be equivalent, so it doesn't matter. The choice is just arbitrary. But it's important to know that as you're choosing the state, you are being guided by your output. What is the variable of the output? In this case, the variable of the output is y of t, which means y of t and its derivatives then could become our states so that the modeling can be easy. Now, so this means therefore that our equation, our ordinary differential equation, can be rewritten as mass times this is y dot dot. Y dot dot is the same as saying the derivative of x1. So x1 is equivalent to y dot dot, because x1 dot is equal to y dot dot, because we are taking the derivative of x1, which is the derivative of the velocity, and this is going to be equal to u as it is minus k, but k times what? K times y, but y, in this case, we have already assigned y to x2, so this becomes the state x2 minus b, b times y dot, but y dot we've already assigned it to state number 1, so this becomes state number 1. So this becomes our first differential equation. Now by definition, we notice that our x, because the differential equation has to be differential equation of both variables, so we need to take the differential equation also of second variable, which is x2 dot. X2 dot, in this case, x2 dot is the same as saying y dot. Y dot has to be equal to x1. Sorry, has to be equal to x1. This is by definition, because we have already defined it here. By definition, judging from this, x2 dot is going to be equal to x1. So those two, this equation and that equation, become our differential equation. And as for the output, remember our output is going to be y of t. So our output y is simply equal to x2. Also, this is by definition. So now we have established a two state differential equations and one output equation. Now, having done that, we have seen that the state differential equation are of the form x dot is equal to some matrix times x plus some matrix times u. So we need to put this, to rearrange this into this form. So having done that, we realize that in fact, this being our equation, we can simply take this first equation x dot, because it does not conform to the standard here that we are putting. So the first few variables have to relate to the states themselves. So we have k minus, we'll have to rearrange this equation. Remember, we are talking about this equation. We have to rearrange this equation so that here we have minus b x1 and minus k x2, and then the last bit of this, it has to do with the input b, and then plus u. Now, if we divide by m on all sides, divide by m, divide by m, divide by m, divide by m, then the m here, this side will cancel, because these two m's will cancel. Then we have the first differential equation is x1 dot is equal to minus b divided by m minus k divided by m times x2 plus 1 over m times u. And then for the second differential equation, the second differential equation is already in that form. Here we have simply x2 dot is equal to x1 plus some constant 0 times u. So that's basically what it is now here. Remember here, this one, the coefficient of u, it's going to be 0, otherwise it's not written here. Remember, we are trying to achieve this representation where we have x dot times the states, a times the states, and then plus b times the u. And then in the second, for the output, what we are trying to achieve for the output is the form y is equal to cx plus du. So it therefore means that y in this case we multiply, it's going to be 1 times x2 plus 0 times x1 plus 0 times u. So it's going to be in that format. Now if we move on from there, this is what I was previously talking about. It means then we can translate these equations to that format, then we can translate that into this format, so that we have our format x dot is equal to ax plus b u, and the output y is equal to cx plus du. So if we look at this equation, we can see therefore that if we look at this equation, we can see therefore that if we look at the output equation, for instance here, let's look at the output equation. The output equation has to be y is equal to cx plus du. Remember, the x here is a vector, so this is simply y is equal to c times x1 x2, so it's a column vector, it's a column vector plus d times u. There's only one input, so it therefore means then that this is equal to y is equal to a vector c multiplying x1 x2 plus a single digit d multiplying u. because of the sizes of the matrix. Remember our matrices, if we have a 2 by 1, it will need to be multiplied by 1 by 2, so that the output is 1 by 1. The output is 1 by 1. So in this case here we have a 1 by 1. We'll need to multiply it with a 1 by 1, so that our output is also 1 by 1. So recall that manipulation of matrices. Therefore, if we look at this, we see the coefficient of x1. Remember, when you multiply, it's going to be row by column. So the coefficient of x1 is 0, and the coefficient of x2 is 1. Here it is, x2. And then the coefficient of u is 0. Therefore, we have got our D matrix here. The D matrix is 0. The C matrix is as follows. We can do then the same. We can follow the same approach. We can follow the same approach with our A, the differential equation here, A. So we said the differential equation is going to be x dot is equal to A x plus BU. Remember, x dot is simply x1 dot, x2 dot is equal to A times x1, x2 plus B, which is times U. So now if we look at the dimensions here, the output here is 2 by 1. So for us to get an output of 2 by 1, we know here we are multiplying a 2 by 1. It has to be multiplied with something, with 2 something here. But the result has to be equal to 2 by 1. So which means the A matrix is going to be 2 by 2. And then here the U is 1 by 1, which means the C matrix has to be 1, such that there can be multiplication. But since the output is 2 by 1, it means this has to be 2. So if we look at this equation, these two equations here, starting with the bottom one, x2. So this is x2 dot. x2 dot, we see that x2 dot has to be equal to, remember it's row by column. x2 dot is going to be this row by this column plus this row by this column. So in actual fact, here for what multiplies u is going to be 0. So this, we'll put 0 here. And then for this row, we have the coefficient of x1. Coefficient of x1 is 1, so we'll have 1 here. The coefficient of x2 is 0, so we'll have 0 here. So that makes the bottom of the A matrix. And then if we look at the first line here, x1 dot, we look at the first row, which corresponds to this equation. Now the coefficient of u here is 1 over m, and the coefficient here, we're going to look at the coefficient of x1 and the coefficient of x2. Coefficient of x1 is like this. It's b over m, and it's minus k over m. So therefore, the B matrix here, sorry, the A matrix would be as given here, and the B matrix will be as given here. And in this case, this becomes our state variable representation of the system, or the state space model. So we have achieved that now. Now, let's look at how we linearize our system. So remember linearization, what we are saying is we have this nonlinear generic model. We want to present it into this linear generic model using the new variables x bar, where x bar is equal to x minus x0, where x0 is the point of linearization, and u bar is simply equal to u minus u0, where u0 is the point around which we will linearize. Now, the linear version of this model is obtained using Taylor series. So with Taylor series expansion, we said you take the first derivative of your function with respect to the variable, and then you assign the values of that derivative at that point, x0, u0. You take this plus dg du at the equilibrium point, or the point at which you are linearizing. Similarly, for the output, you're going to take the derivative of f with respect to x at this point, and then you're going to take a derivative of f again with respect to u at that point. So in this case, what tends to happen then is that the new a is going to be equal to the derivative of x with respect to g at the point of linearization, and b is going to be the derivative of g with respect to u. C is going to be the derivative of f with respect to x, and so on and so forth. So that's simply how you linearize using the same Taylor series expansion. Now let's say we have the following single input, single output system with just one state variable x, and we want to find a state variable a linear state variable representation around a fixed point. This point is x0 is equal to 2, u0 is equal to 3. So we have here a state differential equation as well as your output. Both of these are non-linear. You see that differential equation is non-linear in the state, but linear with respect to the input. The output is non-linear with respect to the input as well as the output. Now we assign the new variables. Remember, we're going to have y bar and u bar as well as y bar here. X bar, u bar as well as y bar. Now we said the A matrix. The A matrix is simply calculated as dg dx. This is our g function. This is our f function. G of x, comma u. This one is f of x, comma u. So we take dg dx dt, and g dx dt is which means our g of x in this case is 3. Our g is simply equivalent to x cubed plus 2u. So if we take x derivative of this with respect to x, the derivative here becomes 0. This becomes 2x squared. 0 plus 2x squared. Now this is what we get, and then we evaluate that 0 plus 2x squared at the point x0, u0, and because x0 is equal to 2, this becomes 3 times 2 squared, which is equal to 12. So that's how you get 12 here. And then in a similar manner, you take for the b function, you take dg du. So if you take u, it's x cubed plus 2u. So you take the derivative with respect to u, this derivative will be 0. This will just simply be 2, and at 2 it remains at 2. For the c value, sorry, for the c matrix, you have the derivative of f. F is equal to x u. You take the derivative of x with respect of f with respect to x. What remains then, it becomes u, and then you substitute for that u, you substitute the value at equilibrium, which is the 3. Here you take the derivative with respect to u, and then you are left with x. You substitute the value, it becomes 2. Now this means, therefore, you can rewrite your equation here as a x dot is equal to ax plus bu, and the output is y is equal to cx plus du. Now, if you substitute here, in this case, this is your state variable. You substitute your a is 12, plus your u, you substitute your b. Your b here, it's 2. As you can see, your b is 2. So you substitute 2 there. Your a is 12, substitute 12. And in this case, you have your c as the output here. So your c is 3, therefore it means this becomes your c. And then you have your d is 2, and this becomes your 2 here. So this then becomes a linearized single output, single input system with a single state. Now, there is a way in which, under suitable conditions, we can convert from a generic state variable form into the transfer function model. The reason for this is we've got a lot more tools showing how we can solve, or we can analyze control systems using the transfer function model. So sometimes we may need to convert from the state variable to the transfer function. Now, the state variable can be converted assuming 0 initial conditions. That is, the derivatives are 0. The initial conditions for all the derivatives of the state are 0, as well as the initial condition of the state itself is 0. And the way in which we convert is that the transfer function g of s is simply equal to this summation. Is simply equal to c times s times the identity matrix minus a, all of that inverse, times b plus d. So that's how basically you convert from a state variable to the equivalent transfer function model. Let's look at a simple example here. A simple example of a single state seesaw system that we have just linearized. So in this case, we know that a is 12, b is 2, c is 3, d is 2. And our identity matrix here is simply the number 1, because these are 1 by 1 matrices. Now, it therefore means we said, now, if we have such a system, then its transfer function g of s is going to be c times the inverse of si minus a times d times b plus d. So if you substitute for all of those values into this, you can substitute for c3, you can substitute for I, you can substitute 1, you substitute a, which is 12, b2, d, we substitute for b2, and d is also equal to 2. So what we then do is this therefore means that s minus 12, it's the inverse, so it's 1 over s minus 12, 2 times 3 on top, plus the d, which is 2, and this gives us that 6 over s minus 12 plus 2. And if you do that computation, this is the same as saying 6 plus 2s minus 24. S at the bottom is s minus 12. And then this gives you a system like this, whereby you have a pole, you have a 0 at s is equal to positive 9, and you have an unstable pole here at s is equal to 12. So this is the transfer function equivalent of this state space. Another more interesting example here would be when you have a two-state system, which is a seesaw, and you have, in this case, a 2 by 2 matrix as an A, and a 2 by 1 as your B, and then your C it's a 1 by 2, and the D here it's simply 0, which is not written. So we have the A matrix, the B, the C, and the D. And your identity matrix becomes this 2 by 2 identity matrix. Remember we said then the transfer function model should be of this form. Now, having just revised what how to manipulate matrices, we can start by tackling this inner product here. Si minus A. Si minus A will simply be S times the identity matrix minus the A matrix. And then remember, with matrices addition and subtraction, you add and subtract the corresponding members. So the S gets multiplied out to all the elements, and then this will give us Si will simply give us S0, 0, S. Now if you minus A, then you will get, here you're going to get S minus -1, which is S plus 1, and then you're going to get 0 minus -2, which is positive 2, and then you're going to get 0 minus 1, which is -1, and you're going to get S minus 0, which is S. So this becomes that. But now we need to take an inverse of this. So the first thing before we take an inverse is to determine what the determinant is. So the determinant is simply the multiplication of the leading edge, which is S plus 1 times S, S plus 1 times S, minus the lagging, minus this lagging edge, which is 2 times -1. And then if you make this calculation, you see that this gives you S squared plus S plus 2. Now recall, we said if you have a matrix X and then you wanted to take its inverse, what you're going to do is you're going to swap the elements of the leading edge, and then you're going to negate the remaining, and then you multiply by the determinant. So it therefore means if we take the inverse of Si minus A, this will simply be 1 over the determinant times we swap this. We swap S plus 1 and S, and then we negate the remaining. And then in that case, you will get, in that case, then you get your inverse. Now, to do a final calculation then of the transfer function model, you will multiply that by C, and then later by B, and then you add D. In this case, our D is already 0. We know that the D is already 0. So when we carry out the multiplication,
take you back one calculation that we need to do, that is to calculate this matrix arithmetic. So we already know that this is the value of C. This is the determinant, and together with this they make up the inverse, and then this is B and this is D. So to compute the matrix multiplication, we take these two matrices together and we multiply a row by a column. So we take the first row with the first column, which gives us S times 1.5, -1.5 times S, -2 times 0, which gives us 0. And in the next calculation, we have the bottom row, still the column of A, we have 1 times 1.5, -1.5, and then we have S plus 1 times 0, which gives us 0. And then that computation together gives us -1.5 S, and at the bottom it's -1.5. Now the next calculation would be to do this single row by that column, which is the next multiplication. So we have 0 times minus 1.5s plus 1 times negative 1.5, and then all of that gives us, because this one becomes 0, it gives us 1 times negative 1.5. So we have negative 1.5, because this is 0, it falls off. And then so it means therefore our transfer function finally becomes negative 1.5 on top, and at the bottom the equation becomes s squared plus s plus 2. So this is the transfer function. So we have successfully been able to convert this state space representation into a transfer function representation. And the way we do it, we have said, is to use this computation that shows how you can compute the transfer function using the A, B, C, D matrix and the identity matrix. So be sure to try some of the examples, which are some of the problems which are given in the tutorial, just to get the practice. The reference book chapter 3 of that at the end also has some exercises which you can do to practice this computation. Now, it therefore means that at this point in time, you should be able to understand the elements of the state space or state variable system representation. You should know what the state variables are, what is the state differential equation, what is the output equation, and you should be able to convert the differential equation or the transfer function model to a state space representation. And you should also be able to convert from a state space representation to a transfer function model.